Okay, welcome to the Bhaumik public lecture. We are really delighted to bring the most interesting theoretical physicist to UCLA. Professor Susskind is currently the Felix Bloch Professor of Theoretical Physics at Stanford. He's a world-renowned physicist. He's made many important contributions, including being one of the founding fathers of string theory. He's known for the Holographic Principle, which I believe he will say something about, the string theory landscape. He's won many prizes. That includes the J.J. Sakurai Prize in 1998, the Pomeranchuk Prize in 2008, the Oscar Klein Prize in 2018. I think we can predict when we get another big prize. I have another big prize. And I have to, another 10 years ago, another prize. It's been happening like clockwork. Also, he's won the American Institute for Physics Science Writing Award. That's for his popular books. He's the author of The Cosmic Landscape, and my favorite one is The Black Hole Wars, my battle with Stephen Hawking to make the world safe for quantum mechanics. And today he's going to tell you about gravity and its quantum origins. So without further ado, I give you Professor.
Okay, thank you, Steve. Oh, you know what you forgot? Los Angeles Times, best nonfiction book of the year.
Well, you know, it's not on your Wikipedia.
No. Two things. They also have my birthday room. Okay, so first, I have a computer that I usually put my talks on, but I always worry that the computer's not going to work because the computer belongs to Google. And, you know, Google computers and stuff like that often don't work. Why does it belong to Google? That's a long story. Don't worry about it. But in order to make sure that I would have the talk available in case the Google computer didn't work, I sent it to Tzvi by email. This is Tzvi's computer here. But then when I got here, in fact, the Google computer wouldn't connect to the internet. After a while, I realized this was part of Google's protection to keep me from giving away Google secrets, which I have none. But the result of that was I didn't have the talk in front of me for the last 20 minutes because he screwed up and lost his computer and finally found it. And you know, during that period, I was going to study the talk and try to remember what I was supposed to say. Well, the result of this is that every new transparency will essentially be as new to me as it is to you. So, here we go. I'm going to tell you basically the thoughts, but they're the thoughts not only of myself, but I think of a growing community that originated from the string theory, well, originated from several communities. String theory community, quantum field theory, condensed matter physics, and lately the quantum information and quantum computing community, which are all talking to each other in remarkable ways at the present time. And the thesis of my talk, which, as I said, is a growing view of a whole community of physics. They call the it from qubit community. It from bit was a John Wheelerism to describe how physics might emerge from information theory, and it from qubit is its modern quantum version. There's a whole bunch of us that consider ourselves, we call ourselves qibitzers. And the things I'm going to tell you about are sort of the collective thoughts of many people. Unfortunately, Joe Polchinski is no longer with us, but he certainly contributed a great deal to my thinking about these things. Juan Malvasena, for sure. Those names may not mean too much to the non-physicists, but I can tell you that the physicists in the audience not only know them, but consider them some of the greatest physicists in the world. But the thesis of the talk is that the origins The origins of gravity are really to be found in the principles of quantum mechanics. Now, let's talk a little bit about what is called quantization. Quantization is a procedure for starting with a classical theory. For those who don't know the terminology, a classical theory means one without quantum mechanics. To turn it into a quantum theory, the theory of some phenomenon, classical, can be turned into a quantum theory of the same phenomena by a process that's called quantization. The process was invented by Paul Dirac sometime around 1930 or 29, I'm not sure exactly when, maybe it was 28. And it consists of a sequence of rules. You take the equations of motion of the classical theory and you apply quantization to them, and you get the quantum theory of the same system. Examples: the harmonic oscillator, which is just a vibrating spring, if you like. That takes the classical theory of vibrations and replaces it by a quantum theory in which the energy levels come in discrete units being Planck's constant h times the frequency of the oscillator. That's just one example. We apply the same rules to the hydrogen atom. Now, what is the hydrogen atom? The hydrogen atom is a little planetary system where the electron moves around the nucleus according to Kepler's laws, if you like. You apply to the classical theory of orbits the quantum rules that Dirac prescribed, and what do? You get a theory of quantum hydrogen, the correct theory of quantum hydrogen, which contains everything that was known about the spectral lines of hydrogen. In fact, if generalized a little bit, it becomes the theory of all atoms, the quantum theory of all atoms, and underlies all of chemistry. Highly successful theory. Quantum electrodynamics. Electrodynamics is another example. Electrodynamics is a classical theory, the theory of Maxwell's equations and so forth. It describes electromagnetic waves. That picture there is supposed to be an electromagnetic. I didn't draw the picture, I got it off the internet. It's a picture of an electromagnetic wave propagating E and B fields, electric and magnetic fields. And when you apply the rules to electrodynamics, you get quantum electrodynamics. In particular, photons. Photons and all of quantum electrodynamics come out of this procedure. It was natural when people started to think about the quantum mechanics of gravity to do the same thing, to try to do the same thing. To quantize what is the classical theory. The classical theory is Einstein's theory of general relativity. Apply the quantum rules to it, and you get out quantum gravity. Or so it was thought. Well, it didn't work. You got a mess. You got a mess full of mathematically awkward at best and often inconsistent equations. Everything came out infinite or zero. Things which shouldn't be zero or shouldn't be infinite came out that way. And the result was highly non-satisfactory. What was wrong with it? Well, I think, and many of my colleagues think, that the mistake was that quantum gravity is a more fundamental thing than either quantum mechanics or gravity. And in separating it, in pulling it apart into a classical theory called general relativity and quantum mechanics, a basic mistake was being made that quantum mechanics and gravity are so closely connected that tearing them apart into two separate things and then putting them back together again was the fundamental mistake. So I'm going to tell you some of the connections between gravity and quantum mechanics that makes me and many of my colleagues suspicious that really the rules of gravity come out of quantum mechanics, and not that you take gravity and quantum mechanics and combine them through this somewhat artificial procedure, which, as I said, led to disaster. Yeah, the principles of quantum mechanics and gravity seem to clash, and no clash is greater than when you try to apply quantum mechanics to black holes. That is where, as we used to say in the Bronx, am I allowed to use a Bronx expression? That is where the shit hits the fan. talk about black holes, and let me tell you what the problems were. That's a lovely picture. Can that be seen? That's clear, isn't it? From my position over here, it doesn't look too clear, but I have it on here. All right, that's a picture, a fictitious picture of a black hole. Black holes are really things which exist in 3 dimensions. In this picture, the black hole is a 2-dimensional creature. It looks like a bathtub drain or a drain of some kind, where fluid would just go down the drain. And in fact, in many ways, black holes do behave like drains, with the water going down the drain in such a way that when you get to a certain place called the horizon, the water is moving inward at the speed of sound. Now, in the real case of a black hole, it's the speed of light, and it's not water, it's space itself, which is being sucked into the black hole in such a way that a horizon exists, and the horizon is this red circle here. It is the place where the velocity of infall becomes equal to the velocity of light, and therefore nothing from within that horizon can escape, for the simple reason that it would have to exceed the speed of light relative to the inflowing space in order to get out. That's a simple picture of a black hole. The horizon could also be called the point of no return. Once you cross it, you're doomed. If you don't cross it, you might fall in, but you can also try to escape. That's the simple theory. That's black hole physics in a nutshell. Well, not quite. Now, imagine we throw something into a black hole. In this case, it's an orange. We throw an orange into a black hole, and we watch it from the outside. We have a telescope which allows us to watch it from the outside. And what we see is not the orange crossing the horizon, but asymptotically getting closer and closer. As it falls in, the motion slows down. Anything having to do with the internal dynamics of the orange slows down. And the orange appears to Lorentz contract. It appears to pancake, become thinner and thinner as it approaches the horizon. And it takes an infinite amount of time for it to cross the horizon, as seen by a telescope from the outside. In fact, any experiment that's done on the black hole and matter falling in, which is done from the outside without itself falling into the black hole, will be consistent with the statement that the orange never crosses the horizon, but simply gets pancaked into a thinner and thinner layer. In fact, since we can't see light from inside the black hole just appears black. And so what we see is this black object with an orange falling toward it and asymptotically getting closer and closer. Well, in fact, it's more weirder than that. All of the matter which fell into the black hole, which created the black hole in the first place, the star, gas, whatever it was that fell into the black hole, also never crosses the horizon and accumulates, at least as seen from outside, it appears to accumulate in a sort of sedimentary layer that gets closer and closer and closer and closer to the horizon, getting thinner and thinner and thinner, but never crossing it. Now, this has not got to do with quantum mechanics, and it's not controversial. This is a standard aspect of black hole physics. But what is peculiar is that if you yourself, with your telescope, with your spaceship, whatever it is, also fall with the orange into the black hole, you see the orange just cleanly and smoothly passing the horizon with nothing special happening. Now, this is a very peculiar tension between what's seen from the outside and what's seen falling into the black hole. And this led to very big puzzles when quantum mechanics was applied to the system. So let me tell you, that's about all I have to say about classical black holes for the moment. When quantum mechanics was applied to black holes, a discovery was made. It was made by a physicist named Jacob Bekenstein and then elaborated on greatly by Stephen Hawking. It's that black holes have entropy. What is entropy? Entropy is hidden information. I'll give you an example, a bathtub full of water. The bathtub full of water has only a couple of properties that are of interest to you. You want to know what its temperature is, you want to know what the volume of the water is, that's about it. You don't need anything else. But there's an infinite, not an infinite, a large amount of information stored in that bathtub. For example, just the position and velocity of every molecule. But the molecules are too small to see, and they're too numerous to count. And so all of that hidden information is summarized by saying the bathtub full of water has entropy. A black hole also has entropy. Why does it have entropy? Because all of that matter that is accumulating closer and closer to the horizon, which becomes incidentally more and more difficult to see, carries information. That information is hidden. And because of that, black holes have entropy. That was the great discovery of the early 70s. And it's dominated physics ever since. Okay, now, what was discovered was very surprising and peculiar. It's that the entropy, S stands for entropy. Entropy, sound it out. Entropy starts with S, right? I do not know how S got to be entropy. But S is entropy. But, oh no. Gee, your computer has screwed up. All right, so that, yeah. All right, read that. Yeah. Okay. Yeah, but I'm afraid it's going to come up more. The entropy is the area of the horizon of a black hole. I think there's a speed of light cubed, there's a Planck's constant in the denominator, and there is a Newton constant, gravitational constant. Now, a number of things peculiar about this. First of all, C is a huge number, H bar is a tiny number, and G is a tiny number. That means the entropy is enormously large for a given area. But what is also was very disconcerting about this formula, I remember when I first saw it, it sounded crazy, because in all other areas of physics, the entropy is always proportional to the volume of a system. How much information can you hide in this room? Well, basically a bit of information in each little unit of volume. And so, in all previous physics, the formula entropy is proportional to volume would have surprised nobody. But the idea that the entropy, all the hidden information that you can store in this black hole is associated with the bounding area was surprising. Yeah, let's go on. All right. So the black hole stores information on its boundary, on its horizon, not in its bulk. Well, the next discovery was Hawking's. It was 1974, and what Hawking discovered is that black holes evaporate. Here's this is the way I make videos, not videos, but animations. Okay, 1, 2, 3, 4. You see a number of them like that. This is my low-tech way of making the animations. The black holes evaporate and they disappear over a very long period of time. The question is, what happens to all that stuff, all that information, that hidden information that was stored just adjacent to the horizon? Hawking said it disappears. Other people, like myself, Ferrara-Tuch, said, no, it can't disappear. That violates the rules of quantum mechanics, and indeed it does. The rules of quantum mechanics say that information never disappears. It may be radiated out or into the great yonder in the form of Hawking radiation, or an evaporating bathtub. It would be radiated out in the form of the evaporating molecules, but information never disappears. This was a paradox. And why was it a paradox? Because anything that falls into the black hole cannot come out. Why not? It has to exceed the speed of light. So this was a conundrum, a problem, how to reconcile the basic quantum mechanical rule that information is never lost with the idea when something falls into a black hole, it's gone forever. Okay. That led to something called the holographic principle. I'll say it in as simple a way as I can, that the horizon of a black hole, in some sense, is a hologram of everything that falls into it. A hologram is a two-dimensional, a real hologram. Ordinary hologram is just a two-dimensional piece of film, And on that piece of film is stored all of the information that is encoded in three-dimensional space. So it suggested itself that in some sense the horizon of the black hole is a kind of hologram that stores all of the information that actually falls into the black hole, and that the paradox is resolved by saying all of the degrees of freedom of everything inside the black hole are really stored and counted as degrees of freedom on the boundary of the black hole, the horizon of the black hole. But it went further than that. Let's see, we still have the same problem. S is less than. Another fact of black holes is they are the densest things in the world. And because they are the densest things in the world, they store the maximum amount of information in a given volume. What that said is that the maximum information that you can store in a volume, whether or not there's a black hole there, is never bigger than the bounding area of the region of space. It is as if to say, all of the information contained, you, and you, and you, and you, and you, and the seats and everything else in the air molecules can really be represented as information on the walls of the room. That principle became known as the holographic principle, and what it says, which was very odd and thought to be somewhat crackpot when it was first put forward, is that a theory of quantum gravity in this room, for example, should be formulated as a theory of degrees of freedom that live on the walls of the room, not the volume of the room. That holographic principle started out, as I said, a little bit, some people thought that the authors of it too. The authors of it were fairly famous physicists, and they were considered pretty good physicists. But a lot of people said, oh dear, they lost their marbles. Over time, the holographic principle has gone from being a wild speculation to something a little better than a speculation, called what's better than speculation? A conjecture. And then from a conjecture, it became a principle, and from a principle, it became a working tool. When a thing goes from a wild conjecture to being a working tool that actually can be used for things, that's of course a good thing. How did that happen? That happened as a consequence of the work of one Novosena, who found an extremely precise version of the holographic principle. Mathematically absolutely precise, and it is, again, it has dominated physics for the last 20 years. It is called, and the term doesn't have to mean anything to you, it's called ABS-CFT. Don't worry about what ABS means, don't worry about CFT means, but it's a theory of gravity in a kind of bounded region of space. It's the soup can there. The soup can has a boundary, which is the label. It has an interior, which is the soup. And incidentally, in this picture, the vertical axis is time. So this is time, the horizontal directions are space. The soup is the bulk, degrees of freedom, is what's inside the room, so to speak. And the boundary is the label where the holographic description of the system is stored, mathematically stored as information on the boundary. Malvacena's construction was so compelling that by the time it had been absorbed, the holographic principle was accepted as a genuine principle. Okay, so let me give you some examples of the sorts of things that the holographic principle says. Let's take the boundary theory. And incidentally, the boundary theory for the technical experts is a quantum field theory that lives on the boundary. It's as if quantum field theory lived on the walls of this room and nevertheless describing everything else. And you take that boundary field theory and you heat it up. You heat it up by dumping energy into it and creating heat. That is what the boundary theory is. What is going on in the bulk? What's going on in the bulk is that heat is described as a black hole. The dark region in this picture here is the black hole. It's evolving in time. And on the boundary description, the mathematical equivalent of that black hole in the boundary theory is just heat, which means lots of particles, photons, not photons, we call it gluons, but lots of particles on the boundary describing the same physics as the black hole. And that's been highly tested, incidentally. This is very well tested. Okay. The lesson is that somehow the quantizing of general relativity in 3 plus 1 dimensional space, that means 3 plus 1 dimensions means 3 dimensions of space, 1 dimension of time, instead of quantizing gravity in 3 plus 1 dimensions to get quantum gravity, we do something entirely different. Quantum gravity emerges out of the ordinary quantum mechanics of a 2 plus 1 dimensional theory, and that means the theory that lives on the walls of the room. This was a surprise, and it is, as I said, I've emphasized over and over that this is now a working hypothesis and even a tool of theoretical physics. Well, let me give you another example of a connection between quantum mechanics on the boundary and the bulk physics inside. Let's suppose somebody came and tapped on the boundary. You can think of that, forget tapping on the boundary, throwing in a particle into the boundary, hitting the particle with a high-energy photon or something, or not even a high energy, just a photon, from the outside. Okay, what happens? It excites the boundary theory, and it creates these gluons. At first, it creates a pair of fairly high-energy gluons. Now, I'm telling you, this is a property of basic quantum mechanics, or the quantum mechanics of many body systems, or complicated systems. And what happens after that is the degrees of freedom which carry that information start to split. They start to split, and they start to evolve into more and more. This is a well-known process in quantum field theory. It's called jets, or whatever, where a high-energy particle will fragment into many, many, many more of them. It's very similar to what happens when a cosmic ray comes into the atmosphere and creates a big shower of particles. And the number of gluons after a certain period is called the size of the perturbation. The size of the perturbation turned out to be connected with an entirely different quantity that describes not the boundary theory, but the bulk theory. In throwing in something into the bulk, we threw in a particle, effectively. We threw in a particle, and that particle started to move toward the black hole. Under the influence of the gravity of the black hole, that particle was accelerated. Its momentum began to increase. One thing that was discovered is the equations of motion for how the size of this bunch of gluons evolves in time is exactly the same as the equation of motion for the momentum of the inflowing particle that it's describing. In other words, to put it another way, I think I did put it another way on this slide. Yeah, as I said, I really don't even know what's in this slide. I have to read it myself. The gravitational attraction, the pull toward that black hole, is nothing but the quantum mechanical tendency for perturbations to grow and diffuse and develop into these larger and larger perturbations. So I'm not going to explain these things in great detail. I want to give you the flavor of the ideas. Again, another basic gravitational idea. In this case, nothing but gravitational attraction becomes related to the quantum mechanical tendency for perturbations or operators to grow. So this was yet another example. Now, how special are these holographic quantum theories on the boundary of space? Are they very, very special? Are they somehow something unusual that we've never seen before? And the answer is largely no. They're more or less, now the experts here will laugh when I say this, but they're more or less garden variety standard quantum mechanical field theories. Quantum mechanics on the boundary. The one thing that they don't have is gravity. They do not contain gravity in their formulation, and yet they lead to gravitational interactions in the bulk. So one might say then that in these theories, gravity or gravitational interactions and so forth are emergent. They emerge out of the evolution of the quantum system describing the holographic system. This was, again, And I don't think it's fair to say that everybody agrees with this, but everybody that I talk to agrees with it. No, everybody I will talk to agrees with it. All right, let's come to another basic quantum mechanical property. Entanglement. How many people here have not heard of entanglement? Oh, wow. Okay. How many people understand entanglement? Good. You with me? Entanglement, I love this word. I've never used it before in my life. Quintessence. The quintessence of quantum mechanics. All right, so let me give you a little bit of history about entanglement and other things. 1935. By 1935, Einstein was considered a very spent force. He was considered old. Not as old as me, but old. 1935 was a very, very good year for Einstein. He wrote 2 papers which are absolutely seminal for what is happening in physics today. And in some sense, they may have been some of his deepest discoveries. The first one was with Podolsky and Rosen. It's called EPR, and it's all about entanglement. It was really the first real discovery of the phenomenon of entanglement, which we'll talk about in a minute. And the other was a paper on something called Einstein-Rosen Bridges, which we'll also come to. The first paper, EPR, was a purely quantum mechanical thing. The second one was purely about solutions of the gravitational equation, strange solutions of the gravitational equations involving black holes, and they appeared to have nothing to do with each other. I am firmly convinced that Einstein had no idea that these two were connected with each other. There's no evidence at all that he connected the two of them. But you will notice that they occurred about 6 weeks apart. What was he thinking? How did he, why did these two things come up simultaneously in his mind at the same time? I have no idea, but I do not think that he was relating the two of them. Okay, let's talk about entanglement for a minute. What is entanglement? Entanglement is a form of quantum correlation between things. I'll give you an example. This is not real quantum entanglement. Supposing I have a penny and a nickel. Oh, let's make it a penny and a dime because they're about the same size. And I put them behind my back, shake them up, and then give one to Svi and one, who are you? Are you Alice? Johnny? Jean-Luc, okay. You one to Jean-Luc. And I'll let you look at them. You're not allowed to look at them. And then you go out that way, and you go out that way. And what do you know? You don't know anything about what you have because you haven't looked. But then Svi looks at this coin, and he discovers it's a nickel. He instantly knows that Jean-Luc has a dime. Or what did I say? You know, the other one. Instantly. It is as if that information flowed across space instantly. But of course, there was no information that flowed across. Jean-Luc doesn't know what he has. He's just as much in the dark until he looks. Or until he gets a message from Svi, which would take some time. Entanglement is like this, but it's also different. Entanglement between two systems is also a form of correlation, but it's much deeper and more profound in the following sense. I gave you the coin, and I gave you the coin. You didn't know anything, but I might have known. In fact, maybe I did know. I could feel it in my fingertips. So if I didn't feel it in my fingertips, maybe a photon came and scattered off and went off into the atmosphere. Something knows which you had. In the quantum version, which is called entanglement, there's absolutely nothing which keeps a record. In principle, nothing can keep a record of which was which until it's actually looked at. In fact, I'd say it more strongly, an entangled pair of particles, an entangled system, can be something that you know everything that can be known about, and yet you know nothing about the parts. Two systems which you know everything that can be known about, but you know nothing about the individual parts. Now that's crazy. How can a system be such that you know everything possible about it and you don't know anything about the parts of the system? What do you know? You know about correlation. What, in the entanglement case, what Svi and Jean-Luc know is that whatever they see, the other one will see the opposite. So they know correlation, but they know nothing whatever about. And And what's more, they cannot know more. So entanglement is a sort of state of correlation between systems which is much more thoroughgoing than the classical version of it. Now, there's a fundamental theorem about entanglement. People get very confused about this and read all sorts of nonsense in the media about what entanglement is. Entanglement cannot be used to send messages faster than the speed of light. Again, it's the same sort of thing which we talked about a minute ago. It cannot be used by Sri looking at his electron. Jean-Luc doesn't know anything, although Sri may know what Jean-Luc will see. But it doesn't send information faster than the speed of light. It is just this form of correlation. The theorem, which says that you can't send information faster than the speed of light using entanglement, is called the no-signaling theorem. And it's a very fundamental theorem of quantum mechanics. Okay, so we've been through that, huh? Yeah, no-signaling theorem. Another thing about entanglement is it can only be created locally. You have to have systems next to each other interacting with each other to make them entangled, but once entangled, you can separate them. You can separate things to arbitrary distances and they will remain entangled. So, no signaling, and you have to make entanglement locally. This is what we know about entanglement. And here's a picture. I don't know if you can understand what this is. The blue sheet there is just supposed to be space. I folded it over just so that I could put the red PowerPoint on the top and the red point on the bottom close to each other in the picture. But really, you should think of space as just being laid out, and the top red point and the bottom red point are really very far from each other. The dark black line simply means that the two particles at the red points are entangled. There's nothing more than that. That's getting to be a standard notation. If you draw a bar between two things, it means they're entangled. So this is a picture of two entangled particles. Finish with entanglement for a moment. Let's come to Einstein-Rosen Bridges, the other thing that Einstein did in 1935. Einstein-Rosen bridges were a solution of Einstein's equations that basically described two black holes. Two black holes arbitrarily far from each other, but with a tunnel between them. A tunnel, a wormhole, or an Einstein-Rosen bridge. They're all the same things. And you want to get an idea of what this tunnel is like, think of Los Angeles and New York. They're 3,000 miles apart. They might as well be infinitely far apart, but no, not that bad, but they're far apart. Imagine that there was a tunnel, and the tunnel, well, from one to the other, was only 1 mile. Wouldn't that be wonderful? A 1 mile tunnel between New York. The only way, if you don't go through the tunnel to get from New York to Los Angeles, is to go 3,000 miles. But if you go through the tunnel, it will only take you a second or two. These were the kind of solutions that Einstein found. But what he also found is, in fact, it wasn't so easy. That you can't really send things through these Einstein-Rosen bridges. For reasons I'll make clear in a moment, they were called non-traversable. Short tunnels, but for one reason or another that I'll explain, you really can't send things through them. So the dream of being able to exceed the speed of light using entanglement, using Einstein-Rosen bridges was not to be. Well, here's a picture of that tunnel. New York on the top, Los Angeles on the bottom. Space is not really folded, but I drew it that way so that I could put them close to each other with one of these Einstein-Rosen bridges connecting them. Obviously, there was a similarity between this and the previous picture, in which what we were describing was simply two entangled particles. Again, like entanglement, Einstein-Rosen bridges can only be made by starting with things near each other and separating them. It cannot be made just in place between New York and Los Angeles. It can be made by, in Denver, creating a Einstein-Rosen bridge and then stretching it well and then separating the two ends. This led to a conjecture. It was, again, a somewhat outlandish conjecture at first. It's called ER equals EPR. Einstein-Rosen bridges are the same as Einstein-Rosen-Podolsky entanglement. that they really are two faces of the same thing, and that they are not really distinct. Einstein really lucked out that year, because we now believe this to be true. When I say we believe it, I again mean those people who I speak to. Okay, so how do you make an Einstein-Rosen bridge? Here's one way. If, assuming that this ER equals EPR, identification between entanglement and bridges, here's the way you might think. A little red square you can think of as an electron. The little red squares just represent particles, and here there's 1, 2, 3, 4, 5, 10 particles, and they're entangled in pairs. They were created in the laboratory. Somebody's laboratory created these entangled electrons, and they're not that hard to do. Entanglement is not that weird. It's easy to make. In fact, it's hard not to make it. Okay, so we have these 5 pairs of entangled particles, and then what do? We separate them. They remain entangled. You cannot destroy entanglement. They remain entangled, and now what we have is 2 clouds of particles. Well, 5 particles is not a big cloud, but imagine this was a huge cloud of particles entangled with another huge cloud of particles over here, undergoing their own gravitational attractions with each other. Not this attraction, but this attraction. You get the difference? This versus this. They're too far apart to attract each other significantly this way, but the particles over here attract the other particles nearby. And what do? They collapse into a black hole. Each one collapses into a black hole. And what do we have now? We have 2 entangled black holes. Again, this principle of equivalence between entanglement and Einstein-Rosen bridges tells us that those 2 black holes have an Einstein-Rosen bridge between them. That's the content, if you like, of this ER equals EPR idea. But now, can it be tested? Can it be tested? Can 2 observers, let's call them, well, I was going to call them Alice and Bob. I could call them Steve and Jean-Luc, but I'll remember Alice and Bob better. Alice and Bob happen to be stationed near where these black holes are. They suspect that there's a wormhole connecting them, or an Einstein-Rosen bridge. They're in love, but they're thousands of light years apart from each other right now. What can they do? Well, according to the theory, if it's correct, the entanglement tells us there's an Einstein-Rosen bridge there, and so they should be able to jump into that bridge and in a short time meet at the center. We really think this is true. It's crazy, but we really think it's true. So this is a test that they could do, but they cannot communicate it to the outside world. Once they've fallen into their respective black holes, they cannot get the information back out. So the result is they can test it themselves, but they're doomed. They'll shortly expire at the singularity of the black holes, and they can't confirm, or we cannot confirm that they met on the inside. They can meet, but they can't communicate it. Okay, but what about sending a signal through the wormhole from one side to the other, so that Alice, she has a laser. Alice has a laser, and she wants to shine a light beam through to Bob. Can she do that? Not going around the long way, but going right through the wormhole. Well, it turns out, unfortunately, no. These Einstein-Rosen bridges, as I defined them up till now, are what is called non-traversable. Traversal means you can't go from one end to the other. Here's Alice trying to send a red laser beam through the Bob, and here in this picture she succeeds, but in fact she can't succeed. Okay. Why can't she send the signal through? The answer is because the Einstein-Rosen bridges grow with time. They grow very rapidly. They grow so rapidly that it's actually impossible to get the signal through. Once made, the Einstein-Rosen bridges expand and grow. Even though they may start close, they expand and grow. Here's my little homemade video of what happens. We have these 2 wormhole mouths, or black holes, or ends of the Einstein-Rosen bridge. And if you watch them for a while, you're not watching the outside, you're watching the inside grow, like that, to grow. Okay, how does that affect the question of whether Alice can send a signal through the Bob? Here's the picture. Alice is on the left. She has a photon or an orange or a golf ball or whatever it is, and she wants to throw it at Bob, who's also on the outside of his black hole. Well, she throws it, but she's defeated because, as you can see, it's pretty clear why she's defeated. The Einstein-Rosen Bridge grows, and it always grows faster than the speed of light, or the two ends separate fast enough that nothing can go through. That's called non-traversability. Okay. Right here. What is it that's actually growing? It turns out that it is another quantum mechanical quantity, which we won't get into here, but it's a quantum mechanical quantity in the holographic description, which is called quantum complexity. It never was thought to have anything to do with general relativity. It's a computer science concept. It's basically a question of how hard it is to create a state of a system using standard computer technology. It's not the point here. The point is mainly that there is a quantum mechanical quantity which also grows and which is believed to be parallel to the growth of the wormhole. Let's talk about Alice and Bob meeting in the wormhole. Does this growth of the wormhole prevent Alice and Bob from coming together if they jump in at the same time? Here's the video that shows you what happens. No problem. They can meet at the center, but if they do, they can't communicate it. But if they try to send something through the black hole, they're defeated by the growth of the Einstein-Rosen Bridge. So, that is some of the evidence that entanglement and Einstein-Rosen bridges are the same phenomenon. By now, there's lots more of it. Much of it is technical, and I won't try to go through it. But now comes the question. Is it possible to retard the growth of the Einstein-Rosen bridge? Is it possible somehow to do something that keeps it from growing so that we can send messages through it? Turns out the answer is yes. What you have to do, basically you have to take a wire that can communicate some classical information and send it around the long way between the two black holes. And in that wire you have to send back and forth what is called classical communication. The classical communication is absolutely random stuff. It does not contain any signal at all, in particular about what's going through the black hole, what's going through the Einstein-Rosen bridge. But if you do that, you couple the two black holes the long way around, in fact, that has the effect of preventing the Einstein-Rosen bridge from growing. If it's prevented from growing, that means that you can send things through it. Unfortunately, the effect of this connection and the signals being sent back and forth back reacts on the system, and it slows down, not the growth so much, but the signal going through. It slows it down so much that you can send something through, but it takes at least as much time as it would take to send the signal around the long way. So just by the skin of your teeth, you avoid having contradictions with exceeding the speed of light with all the usual rules of physics, both for entanglement and for Einstein-Rosen bridges. On the other hand, there is something rather unusual about sending messages through the wormhole, what's called sending them through the wormhole. It does not allow faster than light communication, but it does allow something else. It allows perfectly, infinitely secure communication. Communication that cannot be eavesdropped on. In principle, ordinary communication may be very secure. You may use some one-time pad or something to send codes back and forth, which are very, very difficult to decode. But that information about that one-time pad is there. It's there in the atmosphere. It's there in all kinds of forms. And somebody smart enough could tap it in order to be able to decode or to eavesdrop on a message sent through any normal classical communication channel. Sending messages in this way through the Einstein-Rosen bridge is 1,000 million% completely, what's the word, secure. So that has made that is interesting, a new way through wormholes to send information that can't be decoded. Well, is it really new? Is it something which is totally new and totally unexpected? It is not if you believe in this connection between entanglement and Einstein-Rosen Bridges. It is, in fact, a well-known 25-year-old protocol for using quantum mechanics to send information totally securely. It is called quantum teleportation. It has nothing to do with science fiction. It's a real thing. It's already been established. But in the forms in which people have contemplated it, they weren't thinking about black holes. They were thinking about very, very simple systems. The two red boxes are, again, two entangled electrons. The green box is a system containing some information that Alice on the left wants to send to Bob. According to the rules of quantum mechanics, this can be done by a protocol called quantum teleportation, a completely 100% secure protocol. I won't describe it for you. I will just tell you that combining the green and the red box on the left and doing a little bit of hocus pocus that you need to follow a few equations about, you can make the signal or the green box pop out from Bob's side with no possibility of interference, no possibility of eavesdropping. So this very exotic and very strange phenomena of sending messages through wormholes turned out to be nothing but quantum teleportation in the context in which you replace the two simple red squares, a pair of electrons or something, by two entangled black holes. Not only that, in principle, sending something through that wormhole can also explore the wormhole, find out what's going on in the wormhole, measure possible extra particles in there, and so forth. And all of these things have complete parallels between quantum mechanics on the one hand and general relativity or properties of space-time on the other. What do I have to say? Yeah. Okay. As I said, the surprise and the interesting thing is that the protocol for sending things through the wormhole is exactly the same as teleportation. And of course, teleportation was never thought to have anything to do with gravity and black holes, turning out to be the case. Okay. The result of that, and the result of some 5 years of thinking about these things, partly on my part, but on a much larger community, is that, again, ER equals EPR has gone from a wild conjecture to from a wild speculation to a conjecture, and is becoming, again, a tool. A tool, in this case, for using gravity to explore how quantum teleportation works. Quantum teleportation is a possible future technology, and let me go a little further and say all of the things I told you are more than just Einstein-Rosen bridges are equal to entanglement. They do suggest this idea that GR equals QN. So what do I mean by that? I don't mean the equality to go both ways with equal force. I don't mean that GR and QN are exact, GR being general relativity and QN being quantum mechanics. I think there should be somewhere between the equality sign and maybe an arrow pointing from left to right, that in fact the rules of, no, the arrow going from right to left, that the rules of gravity are somehow reflections of the basic rules of quantum mechanics, but in contexts in which the entanglement and in which the system is so rich in degrees of freedom, so many of them, that they form large-scale things like black holes, planets, and so forth. So in contexts where the quantum systems that we're talking about are highly rich, very, very many degrees of freedom, almost hydrodynamical in their nature, quantum mechanics seems to turn into general relativity. Now, is this certain? Yeah. I think so. I think it is. But not everybody agrees. Everyone agrees. Seriously. But It's something that remains to be established with utter full rigor. And it's very exciting. It's a very exciting time to be doing physics now because we are really learning radically new principles. I'll just tell you, in my own experience, when I came into physics sometime around 1960, a long time ago, but not early enough to have been part of the revolution that established relativity and quantum mechanics, not even early enough to be part of the revolution that discovered quantum field theory, finding diagrams, and so forth. So I always felt a little bit of sadness and regret if I hadn't been there when the great conceptual discoveries were being made. I don't feel that way anymore. I feel that what's happening now with our understanding of the synthesis of quantum mechanics and gravity is one of those things which is very, very much going to change our whole way of thinking about physics. And so it's been a pleasure for me to tell you about these things, and I hope you've gotten something out of it. Some of you it may be a little too technical for, others I suspect a little untechnical, not technical enough, but I had to bridge two cultures, and so I tried my best. Thank you very much.
How do we know that the map from the boundary of the space to the interior is bijective? Because if it's not bijective,
I forget what bijective means.
it's like one-to-one.
Oh, that's what I used to call one-to-one, but people corrected me and said that's not bijective. Yeah, it's not. It's probably not. In fact, I think we know it's not. There's a whole literature now that's growing on the connection, on exactly this connection, and it seems that that the description of the bulk, in terms of the boundary, is very, very closely related to quantum error correction. And quantum error correction is a way of, what shall I say, of encoding information in highly redundant ways and non-unique ways. It makes error correction, as I said, is a way of encoding a message redundantly in many more degrees of freedom than you need. And it is not one-to-one. It is not bijective in that sense. It's a very good question. Look up error correction and ADS-CFT if you're really interested.
I'm wondering how this view of gravity indicates why gravity relative to the other interactions is so weak.
Oh, that's a good one. For some reason, I never thought of that. I don't know. Look, part of the reason is somewhat artificial. It's just the fact that the ordinary particles in the world are so much lighter than the Planck scale. But there is still some definite sense that gravity is the weakest of the forces, and I don't know. Think about it. It certainly turns up as something in string theory, but I never thought about it in this context. Thank you for the question.
Let's say Alice and Bob are entangled electrons. And let's say
They are entangled electrons. Okay.
if they're on the
I always think of them as the people observing the entangled electrons, but go ahead.
they're on the opposite side of the Einstein-Rosen Bridge.
Yeah.
Separated. How long do they remain entangled? And isn't that a form of communication that makes it conductive?
Unless they get to directly interact with each other, which they won't do if they're far enough apart, that entanglement is frozen in. Now, Alice and Bob, Alice can communicate with her friend Charlie, who is nearby, her. And she can communicate that entanglement to Charlie so that Bob and Charlie become entangled. That is possible. So Alice will no longer be entangled with Bob, but instead Charlie will be entangled. But the fact that somebody on one side is entangled with something on the other side, that cannot be broken.
Isn't that a form of communication in and of itself?
Well, communication means that you send messages, that you send messages which contain content. It's, there's no way to use that ordinarily for ordinary entanglement to actually send a message. What, all that it says is that if Alice looks at her spin, she instantly knows what Bob's spin is. Bob doesn't know. So that is not communication.
But Bob knows that Alice is spinning,
Bob knows what?
that Alice is spinning.
That Alice
It's a certainty of knowledge. If Alice, if the fact that you have knowledge that something is entangled isn't that a fault.
Communication means communication. You're sending a message from one place to the other. No, there's no communication involved in not what I mean by communication. Well, Einstein.
So besides sending something through a black hole, is there some experiment that
Through a Einstein-Rosen Bridges. Yeah. Is there some?
So besides sending some information through a black hole, is there some experiment that would convince you that this is true?
I think one of the things that I've been thinking about, and other people, I'm not going to try to describe the experiments because they're still being thought about. But one of the things I have been thinking about, both with my students and my colleagues, is how to actually design experiments, not using real gravity, but using tangled quantum computers and simulating quantum mechanically these phenomena, and how to bring them actually into the laboratory. So yes, there are a good number of experiments which are possible. One of them is called the scrambling experiment. It's called scrambling. But yeah, there are other experiments. So a lot of people are now thinking about how to bring them into the laboratory.
If I eventually think of general relativity as emerging from quantum mechanics, then this suggests I should be able to compute the gravitational constant G from H bar and C.
No,
But I don't see how I will be
no,
able
no, it's not something to do. In appropriate units, G, H bar, and C are all equal to 1. They're all dimensional constants which can be chosen to be anything you like. There are dimensionless things, and the thing that makes you think that G, for example, is so small, or that H bar is so small, is that you are so big. The question is not why H bar is so small, it's why you are so big. And I'll tell you the answer. You couldn't have asked that question unless you were at least big enough to have a brain that could conceive of the question. So, no, it is not possible to give a derivation of what the dimensional constant is. All you can do is ask, why do we assign such strange numbers to it? And usually it has to do because we're so big.
In the case of Einstein-Rosen Bridges, completely accepted that as well.
Right.
I don't know what's really going on, but don't you still affect that two black holes? And you want to set one black hole right to extract the information on the black hole.
Extracting information out of a black hole is possible. Classically, it is not possible. Quantum mechanically, it is possible, and it is using something like the a version of the quantum teleportation protocol. But basically, you extract information from a black hole when it evaporates. The evaporation process extracts information out of it. And the evaporation process is, in some ways, in its information content, very closely related to quantum teleportation. The famous paper on this is a paper of John Preskill and Patrick Hayden, who described how you extract information out of a black hole using something very closely related to quantum teleportation.
So, when from Newtonian physics to statistical mechanics, we basically get out of with a particle mechanism. So then we just like build some like basic system, like how we basically make equation.
I'm little hard of hearing. Can somebody, some voices are sort of can
Maybe come closer.
So, are you going from Newtonian physics of Newtonian description of a system?
yeah,
Each particle, like
yes, yes.
to statistical mechanical
Mhm.
distribution.
Mm-hmm.
We integrate out the particle degrees of freedom.
Oh, we ignore part of it. Ignore
With
them.
the temperature and all that. So
Right.
it's like it's going from quantum mechanics to general relativity with thought of something similar, some similar operation like going from
Absolutely, absolutely. And there's an analogy that many people have made, in particular Joe Polchinski and others, between the relationship between quantum mechanics, simple quantum mechanical systems, and the gravitational systems, which is analogous to the relation between simple particle mechanics and hydrodynamics. Hydrodynamics is just simple particle mechanics in the limit that there are a large number of closely packed particles. The principles are the same: momentum conservation, energy conservation, Newton's laws. And it's just in a context where degrees of freedom are so numerous and dense that ordinary particle mechanics evolves or morphs or evolves into hydrodynamics. Now you can ask the question, how many particles do you really have to do hydrodynamics? Yeah. I don't think you need probably more than about 20, frankly. I think if you have 20 particles in a small box and you were to simulate their motions, you would find that you're beginning to see hydrodynamical behavior. I think the same is true here, that the gravity-Einstein equations are very analogous to the hydrodynamic equations, and they obscure what the fundamental degrees of freedom are. They don't even care what the fundamental degrees, just that there are such degrees of freedom. And at the other end of the spectrum, small numbers of particles behave according to the obvious standard rules of quantum mechanics. And you could ask the question, how many degrees of freedom do you have to have before it starts to morph and starts to resemble gravity? I think the answer is probably around 20 again. So I think you can do some of these experiments with quantum computers with maybe no more than 50 qubits. And because it won't look, no more than hydrodynamics, 20 particles is not enough to really be very precisely hydrodynamical, but you'll begin to see the crossover from simple particle mechanics to hydrodynamics. Somewhere, I would guess 1,000 particles is more than enough, way more than enough. 5 is probably not enough. Somewhere in between is the crossover from between them. Does that answer your question?
Okay, so like basically you're saying that gravity is the hydrodynamic method.
I think it was Joe Polchinski who said that gravity is the hydrodynamics of entanglement. Meaning that when entanglement is dense enough and enough of it, the system begins to behave like space-time with roughly gravitational behavior.
Learning will be here.
It's got to.
So, yeah, questions, just come up front. Don't be